previous lecture, somebody have asked about the Poisson and exponential distribution. Also, he asked what is the memory list characteristics of exponential distribution. So we are going to go into some details of exponential and Poisson distribution. So we have to study the Poisson distribution before the exponential one. So I have prepared some additional slides. The Poisson distribution is about the number of occurrences of a specific event in a certain unit time. So it is important to consider the number, not the time. Time is related with the exponential distribution. For example, the number of airplane accidents that occur in a year in Korea. This can be modeled as Poisson distribution. Also, the number of vehicles arriving at a gas station during a certain time. This is also can be defined as a Stochastics, the Poisson distribution. With this distribution, we can find the probability that some numbers, for example, the 3 events will occur in a unit interval with an average number of 5. This kind of probability can be calculated with the Poisson distribution. But this distribution cannot show the exact time when a certain specific event will occur. It's just the concept of the average. Next, in addition to this definition, these 3 characteristics have to be considered. First one is all the events occurring in non-overlapping unit intervals are independent of each other. It means like this. This is the time axis. And if we divide this time in some same interval, let's say it's 1 hour each. And the events will be noted like this. This is the Poisson distribution with the average number of 3. In this case, this first property means that these events these events are independent from the next or previous ones. All the events, those are belonging to a certain specific time period, are not related with the other events. Those are belonging to the other time section. This is the first property. And second property is the ratio of the average number of occurrences of an event with respect to the size of the unit interval is constant. It is like this. Let's say the Poisson distribution with the average number is 3. And it means that any event related with this distribution will occur 3 times per 1 unit time. For example, 3 product per 1 hour. In this case, if we define the time interval as 1 hour, in this case, even though we do not exactly predict the exact time, but in this time period, 3 events will be occurred. This is the fact that we can predict. And if we define this duration as 2 hours, in that case, the events will occur 6 times. So this property means that the ratio means that the ratio between the unit time and number of events. This ratio have to be maintained across all the time period. This is the second property of Poisson distribution. And next, the last one is this one. The probability that the same events will occur in simultaneously is 0. It means that in a certain unit time period, and if the average number is 3, then these events will occur like this. These events have to be spreaded. The last property means that any more than 2 events cannot be occurred simultaneously. This kinds of occurrences is not allowed in Poisson distribution. Is this explanation is it okay? Can you follow me? Okay, this is the definition of Poisson distribution and the core characteristics of a Poisson distribution. And these kinds of Poisson distribution can be defined as this formula. This is the density function. The reason why we define the density is because of the probability variable is discrete. If we define the probability model with the continuous variable, in that case, we have to use the mass function instead of density. And with this, if we know the density or mass distribution of a specific event, then we can calculate the cumulative distribution function. It's like this. It's general definition. If we know the unit probability of this the probability variable, then we can calculate the cumulative distribution with this formula. This is the cumulative distribution function. This relation can be applied all kinds of probability, the stochastic models, and this formula is defined as a Poisson distribution. And the graph that is shown here is the plot of this density function. So, let's see. Anyway, you can see here the trends, the change of the shape with the variation of the lambda. According to the increase of lambda, then we can see the shape is being spreaded. This is because the characteristic of Poisson distribution, the expectation, it means that the average number is lambda, and the deviation is also lambda. So if the lambda is increased, the variation also is increased according to the varying value of the lambda. So according to the increase of the lambda, the shape of the graph is more spreaded. If we compare the graph with the lambda is 2 and the graph with the lambda is 8, the graph with the lambda is 8 is more bigger the deviation compared with the one with lambda is 2. Next, we are going to calculate why the expectation and the deviation is like this. Let's use the note. We have defined this is wait a moment. This is so with this Poisson distribution, we can calculate the expectation, I mean this average number. And this is defined as we do not use the integral. We just use the summation because the probability variable is a discrete one. And also here the x is so the expectation can be defined as the let's use k instead of x, and it has to the density function have to be multiplied by the variable. Can you remember why? No, not remember. Can you see why the expectation is defined like this? The expectation number is calculated from the multiplication of the probability variable and the probability density function. So from this, we can now some mathematical calculation is fine. We have to calculate this, and we are expect it has to be the lambda. So if we divide this like this. We can raise this one. Okay. And now some trick is required in order to simplify this equation. That is like this. This lambda square k, let's split like this. Okay. If we split these two variables, then we can bring out this and this outside. So not. I'm sorry. It's okay. So we bring out this variable and like this. Then we can replace k minus 1 to the k with starting from the 1. So this is change like this. Okay. And now we have to adopt one special function, that is Taylor series. Can you remember that the engineering mathematics? From the Taylor series, the exponential function can be defined as the and this is coming the like this. Okay, so we can simplify this term as the exponential lambda. So final calculation is this, and this is equal to 1. So final output is lambda. By the way, just for common sense, when we study about the complex number, it means that how to calculate the square of complex. It means that any number with this type is not shown. Any number with the complex square, this calculation can be conducted by use of this Taylor series also. Anyway, in this way, the expectation value is calculated with respect to the Poisson distribution. Also, we can calculate the deviation. Can you remember the relation between this deviation and expectation? This relation is like this. Any deviation function is defined as the expectation of the square value minus the square of the expectation. So in order to calculate deviation function, deviation number of the Poisson distribution, we just calculate the expectation of the square x or square k, because we already know this value. Okay, so this deviation now we have to calculate this one, and this one is y d now we have to calculate this. And core calculation method is very similar with the one of the expectation. So I'm not derive the detailed calculation, and I will this calculation and leave you for how this is calculated as the lambda. Anyway, the final result is lambda. So this is the reason why the expectation and deviation is the same in case of the Poisson distribution. Now we are going to the exponential distribution. The exponential distribution is widely used for simplification of actual process. Why the exponential distribution is widely used. First is that it reflects real-world phenomenon well. But this is not the first reason. Most important reason is that because it is easy to analyze the stochastic process. Actually, this is the actual reason for the exponential distribution. It means that in an actual phenomenon, is mostly different from the exponential one. But if we apply the exponential distribution to our problem, then the calculation can be very easy. And most important characteristic of the exponential distribution that it can make predictions that are not affected by time. And this is the memory list property. So let's check this simple example. Someone is visit any building, and there is the lamp or bulb, the light bulb. He goes to the bulb and he turns on the light. And he thinks, how long can this bulb will be on? But he or she do not know how long this bulb, light bulb, was on previously. In actual case, in order to expect the lifetime, the power on time of the bulb, we have to know how long this light bulb was on in previous time. But with exponential distribution, in previous historic records, it is not reflected to the expectation. This means that when this person visit this building and let the bulb on, the expectation remaining time is exactly same with the expectation time of the bulb that are never used. This is the very important property of exponential function. So we call this as a memory list property of the exponential distribution. So let's see some more explanation. So this exponential distribution is the distribution of the time it takes for a particular event to occur, and then the same event to occur again. It means that the exponential distribution let us know or let us predict the time between the event occurrence. That is the exponential distribution. For example, if there is a bus that arrives every 10 minutes on average, the waiting time for the next bus after missing the one will follow and can follow an exponential distribution. And in this case, the expectation, the remaining time is 10 minutes again. And this is not related with the when this bus was started. So the historical records, the previous records is not reflected to the expectation in current time. By the way, in order to get the waiting time for the next event, we have to know how many times the events occur on average in a certain time unit. How many times the events occur on average in a certain time unit. Can you remember what this phrase means? How many times the events occur on average in a certain time unit? What is this? This is the Poisson distribution. Is it right? So the relation between the Poisson and exponential is the reverse. It means that the reverse number of the exponential distribution number is a Poisson. Also, the reverse number of the Poisson distribution is becoming the exponential distribution. Here is this is the Poisson distribution. So if the number of the occurrences of a certain event follows a Poisson distribution, and in this case, the time between events follows an exponential distribution. So these two distribution is linked very, very tightly. And fundamentally, it is same property. Those two have same property. Okay, and this is the shape of the density. Actually, this is more close to mass. Anyway, the density function and cumulative distribution function. I'm sorry, I don't know how to turn off the KakaoTalk in my smart pad, so there comes out so many chatting window. So this is the shape of the exponential distribution. According to the increase of the number of lambda, it means that in lambda, the shape is becoming more the steep shape, because lambda, if lambda equals 3, it means that the target events occurred three times for any period of unit time. In this case, the more events occur in a short-term period, we can predict why this is like this, like as shown in this graph, compared to the graph shape with the smaller number of lambda. Okay, now we also calculate the expectation and the cumulative probability function of the exponential one. How about start after in 5 minutes? 5 minutes break. Okay, start again. The in order to derive the relation between the exponential and Poisson. And firstly, let's define the cumulative distribution function as function large f. And you think this variable x here can be thought as the time variable. And this cumulative function means the probability that any event is occur before time x or time t. We can use x or t or k. It's all the same. We just use let's use k. No, let's use t. So this cumulative function is the probability that any next event will be occurred before time t. And we convert this as 1 minus probability of these events will occur after time t. These two formulation is exactly same, okay? Because the entire occurrence is the 100%, or it means that 1. And here, this is very important. This probability means that the event, let's call this event as x. This is the probability that events it can be written like this. This probability means that the probability that events, the specific target events are not occurred from the period of from 0 to t. And next we can split this expression. No, this. It means that this means that the notation of the event is not occurred is written like this at any time point. So if we split, we can, if we divide this time period from 1 to until the time t as a discrete number, so it can be written like this. The probability that an event will not be occurred at time cross at time 2 until the time is t. Okay. And each expression, what is this? At any point of time, the probability of this event is not occurred. This is the Poisson distribution. The number of events those are occurred in a specific period of time. This is the definition of the Poisson distribution. So each term is reflected as a Poisson distribution. So this can be written as what is the Poisson distribution is like this. And lambda is the average number of the events occurred. So we have to insert the zero number into the K. So this term is also like this. This term is also like this. Why is it like this? Because Poisson distribution is also time independent. So at any period of time unit, all the events, all the probability is the same if the expected events is same. So with this calculation, these terms is like this. This can be multiplied by time t because this whole number is t. 1, 2, time t. So this is becoming this is equal to 1, 1. So this is kind of like this. This is the expression of cumulative distribution function of exponential one. And also this reduction is related with the Poisson distribution here in a mathematical way. And now we can calculate the probability density function very easily because this is the time differentiate this. This is the definition of the definition between the cumulative and the mass distribution. So the mass distribution of exponential is like this. Like this. So this is the exactly same that we have seen in previous lecture. And this is called the probability mass distribution with respect to the exponential distribution. Also, with this definition, we can calculate the expectation of exponential one. This is like it's shown like this. We assign 0 instead of the minus infinite because in here the time have to be greater than 0. So we use 0 instead of minus. And we we apply the integral here. Actually, from here, some what do you call it? The partial derivation. What do you call the? I'll just write it down. The expression. Partial integral method is required here. And this is becoming like this, and this is becoming the 1 over lambda. And this is very the expected result, because the relation between the exponential and Poisson is the reverse number. With the similar way, we can also the deviation with this relation. And very surely, this is becoming the 1 over lambda also. It means that in case of exponential also, the expectation value and deviation value are both same. Okay. I'm sorry, there is some errors here, because in order to calculate this relation, we have to multiply it by probability variable here. And that is the reason why I use this method, the partial integral method. And you may well know why this integral is calculated like this way. Anyway, this is the explanation about the exponential distribution and Poisson distribution. Is it okay, all of you? Who is the one that have asked this question in previous lecture?
윤세용입니다.
이해가 됐어요?
예, 도움이 많이 됐습니다. 감사합니다.
다행이네요. 그래요. 그러면 okay. Now we are returning to our progress. Actually, little time remained today, so we are going to so during the remaining time of today's class, we are going to induce the main parameter, the performance index of most simple queuing model. It means that MM1 model. And we have called this MM1 queuing model as the Markovian process, because this queuing model have the exponential distribution of the arrival rate. And this arrival rate have the memoryless property, that is time independent property. So let's see what is the main parameters with rated with the queuing model. Let's assume the two parameter. First one is lambda. We have seen this lambda in previous. In this queuing example, this lambda is the arrival rate. For example, if this queuing model is kinds of service system that 2 customers per hour is arrived in our system. Also, the service rate mu can be defined as the attributes belonging to the server. So server Q, and here is the arrival rate, and this server have a property of mu, and there is no notation about the capacity size, so the infinite capacity of the queue is assumed. And we use the service rate as mu here, so the average service time is becoming 1 over mu. Also, the average arrival time, the inter-arrival time is becoming 1 over lambda. We have to remember this relation. And there is very important indices. First one is the L. L means that average number of customers or the arriving entities in the system. Or we can replace this, the character L as the WIP in the later induction. Also, if the letter Q is added to this L, this means that average number of customers in the queue, not the system. And also we can write this LQ as WIPQ. This is the same notation. Next one is the W. This W represents the word waiting. And the W means that average time during customer spends in the system. And we can replace this letter as CT. CT means that cycle time. And also WIP means that work in process. This is the cycle time. And if we add the Q to this W, this is the average time during the customer spends in the queue. And also we can replace this letter with the CTQ also. And probability of n customers are in system. We can write this as like this. And the last one, the rho, we call it rho. The pronunciation is rho. this rho means that utilization rate. And this utilization rate can be defined as the mu over lambda. Okay. So with this example, the mu have to be greater or same with the lambda. If the case with that this case, it means that if the arrival rate is greater than the mu, at this case, the special treatment is required to calculate the rated the performance indices. So we will not treat about this case with the greater value of mu compared with lambda. It means that this utilization value may be always smaller than 1 or same. Okay, now let's see how each index can be calculated. I'm going to skip this one. This slide shows the explanation about the Markov chain, but we have already studied what is Markov process. As shortly means the time-independent process. This is defined as Markov process. Now let's see the mechanism of the MM1 queuing system. Now, each circle means that the state of server or the entire system. In this case, we will use this concept, entire system. And each circle means that the state of the number of customers inside of the system. For example, this circle means that the system with the states of 2 customers. And this is the state of the system with n customers. And this relation means that the change between each stage of the entire system, the queuing system. And here is the RA and RE. RA means that arrival rate, and RE is the service So if we use this notation, lambda and mu, this is the same with the lambda, and this is the same with the mu. But in this induction process, we are going to use RA and RE. And in advance, from this relation, we can see, or previously rho utilization is mu over lambda, means that RA over RE. Just to remember this relation. And each the state change rate is shown like this. And because of the memory least property of this exponential distribution. So any state of changes can be assumed as this arrival and service rate in all the change units. So now let's see the first section. And in here, this P0 means that the probability of the state of the customer number is 0. And P1 means that the probability of customer number is 1. And the relation between these two terms can be equal if we multiply the arrival rate and service rate respectively. Because if the change from the P0 to P1, this is triggered by this arrival rate. And also, the change from the state of the customer number 1 to 0 can be triggered by this service rate. So this first equation is induced. And if we go to wait a moment. I'm sorry, I have explained in some wrong way. This equation is related with the state 0, just the state. So the probability of state 0 can be triggered by the change from the P1, state 1, that is multiplied by service rate. And if we transferred to state 1, in this state 1, this state 1 is impacted from state 0 and from the state 2. So left side of this equation is the incoming impact from the state 0 and state 2. So these terms means that the change from this state 0 to state 1, and that is triggered by the arrival rate. Also, this state 1 can be deduced from this state 2, and by the triggering factor is service rate. Can you follow me? Because if the change is the state is changed from 2 to 1, the server have to work, and that server working rate is this RE, service rate. So this left side is the incoming factors in terms of the state 1, and the right side is the outgoing event from the state 1. First one is the outside towards the state 2, and this term is the outgoing events from the state 1 to state 0 with the working rate or service rate. Can you understand? So from the first equation, the relation between P1 and P2, P0 is induced. And during this calculation, RA over RE can be simplified as utilization. Also in next expression, the relation between P2 and P0 can be induced. And the multiplication number is U utilization square. In this way, with the ignition relation, we can predict the probability of the state with the number of customers is n can be shown like this. This is here. And also, all the summation of the probability of each state have to be 1. This is very sure. Is it right? So from this expression, according to some calculation, the P0 can be induced equal to 1 minus U. So now we get the probability of the state of customer number equal to n as n. And we now get the P0 from here. So this probability of state n is becoming like this. Very simple expression. So now we can calculate the expected number of customer inside of the entire system. And this expectation also can be calculated by this relation. It means that the probability variable multiplied by is the relevant probability. It's a very similar definition that we have seen in the induction process of the expectation of Poisson and exponential distribution. So if we replace this Pn with this formula, then we can get this relation. And if you want to know why is it becoming like this, let's calculate quickly. Let's note this as S. And this can be it has to be started from 0. This. And we multiply the n here, u here, like this, minus these 2. And this is like this. Is it right? It's a very simple formula. So this summation is becoming like this. So if we insert here, and this is divided, and final result is like this. This is number. Then we can expect the expected number of WIP, or we have write this as the number of the letter of the L. Now let's calculate the system time. We note this as a CT, or we can use W if we use the previous definition. Here comes out the very famous Richter's law. And here we already calculate this WIP like this. And this is very tricky point of this induction is the throughput. Throughput means that the number of the incoming, or actually by dictionary viewpoint, throughput is the final number of customer or product. Those are serviced or those are manufactured in the system during the unit time. But because we have assumed this relation here, service rate have to be bigger, greater than the arrival rate. It means that utilization have to be smaller than the inter-arrival time. So this throughput can be assumed as arrival rate. Very, very tricky one. But also this is very, very important assumption in our example. And this relation is available only when the service time is greater than the smaller than the inter-arrival time, or the service rate is greater than the arrival rate. So if we insert RA here, then we can calculate the cycle time or the staying time inside of the queuing system. And by the calculation, and we have already known the utilization can be replaced by RA over RE. And from here, this RA and this RA is mutually divided, and remaining terms here are RE, 1 minus U, and 1. And by definition, this RE is service rate. Is that right? And the reverse, or the reciprocal number of RE means that cycle time. And we will use the notation E. Actually, this notation means that some efficient. I will explain what this efficient means later. Anyway, if we define the reciprocal number of service rate, that is becoming the service time. So finally, we can get the cycle time. And also this can be definition of the W in previous slide. So now we get the WIP is U over 1 minus U, and cycle time is TE over 1 minus U. Now it is very easy to calculate CTQ because CTQ is just the same with CT minus the service time. Also, WIPQ can be calculated from the Little's law. Throughput. Throughput is always the same across all the points. In arrival point, or queuing, waiting, or service, or throughput, it means the outgoing rate. All the same, always this is same with RA. So we can calculate WIPQ also. Now we have calculated all the important performance index of the queuing system with the property of MM1. So it's already time over. So this is the calculation of the MM1 model. And by use this relation and this result, we can calculate more complex queuing models with the general distribution. We will study about the other kinds of queuing models in next class.